Does anyone have any questions about the PA2 while I'm handing these out? Questions about second programming assignment? Questions about anything else? There should be some just coming across there. I'll just start a chunk here. Would you mind handing them to her? There's a couple if you need some. Cool. All right. Okay, so on Monday we talked about a calling convention. What was the problem that we observed at the end that wasn't just about the calling convention, but our entire approach for the last few weeks? What was the problem we noticed, or the annoyance we noticed at the end of Monday? Something annoying about the way our compiler works that I pointed out on the chalkboard at the end of Monday. What is that? Remember my laptop died and I just started drawing all over the chalkboard? Yeah. Someone said Valgrind doesn't work with it? Is that what you're going to say too? Yeah, so if we run our programs with Valgrind, we have all of these places, we have all these places where we're doing things like moving into some reference from ESP, some value, whether it's whatever is in, usually whatever is in EAX, because that's what we evaluated, and then we're storing it there. So we have all these statements like this, all these instructions like this, and the way Valgrind works, and this is just an interesting comment about how Valgrind is a sort of very C-specific tool. It assumes that the world looks like C compilers intend it to look. And the status during any function call in a C compiler is that the ESP is pointing at the top of the stack frame and EBP is pointing at the bottom of the stack frame. You can actually use different command line arguments to GCC to make it so EBP isn't used in this way. But the ESP is always pointing at the top of all the stack frames. And any local variables, any arguments, anything that's being used by the body of a function in C is going to be referencing memory in this region. It's going to be referencing memory in this stack frame. And so any reference to memory up here, whether you're reading from it or writing to it, is what Valgrind says is, well, you must have gone like out of bounds on an array that's on the stack. You must have just kept going past the end of an array on the stack, and now you're reading memory that you're not supposed to. That's not something that was set up for you to read. So this will cause invalid read and invalid write errors in Valgrind because it's making this assumption. Now, there's nothing like our compilers produce correct answers, right? PA1 and PA2, we were able to write compilers that produce correct answers. They're just violating this assumption of Valgrind. It's useful for us to understand that this assumption about C sort of permeates many modern tools. And sometimes it's nice to play within those rules, right? Because we get the benefit of some existing tools. If we can make it so that our compiler always writes to addresses that are at ESP or higher, we'll get this guarantee that tools like Valgrind will work and report errors if we go outside that range. Okay? So it's just like a nice comment about working with real-world tools, and it'll also let us compare what we're doing with our calling convention to what C does. And so what's on the worksheet today is I implemented a compiler with a particular calling convention. It's different than the calling convention we talked about on Monday slightly. And we're going to talk about the work it does to set up ESP correctly. And I'm not just introducing this calling convention for fun. I mean, it's pedagogically relevant for you to learn that there are different calling conventions in the world. There doesn't just have to be one. But also, I'm going to argue on Friday, I think on Friday, it might go into Monday, that this calling convention is better than C's calling convention for a particular use case. Right? There are actually reasons why the calling convention I'm going to introduce is better than C's calling convention. I'll make a concrete argument for why it's better. Okay? So with that, I want to sort of treat this lecture as a bit of practice for you. Actually, the kind of thing that's on this worksheet is the kind of thing I like to put on exam questions, so that's good practice for you too. So there's going to be a lot of reading what's on this worksheet. We're going to be pretty focused on this worksheet today. And so there's the definition of abstract syntax that includes applications and definitions. There's a sample program in the top middle, and then some stacks and then some generated code at the bottom. So we're going to sort of work through this with questions so that we think about each piece of it. So the first thing, I want to ask this question just to make you read through everything. Which of these is not true of the compiler that's sort of described on this worksheet? So read through the worksheet, see if you can figure out which one of these things is not true. I have extra worksheets if anyone has come in and needs another. Anyone need a worksheet? Raise a hand. Okay. Oh, awesome. And if you find one thing that's not true, look for the second thing that's not true. Okay, 5, 4. I'm going to give you a chance to talk about it. I just want to get this first round in. 3, 2, 1. Okay, so first round, I mean, that was as much of a speed reading test as anything. Talk about this for a minute. Talk about it for a minute. Come up with what you think there's two things in here that aren't true. There's two things in here that aren't true. Okay, take another 20 seconds, and then I'll close this reclick. 5, 4, 3, 2, 1. Okay, A I put up here mainly so that you could, to prime you for looking for all these places in the assembly code. So the assembly code in the bottom right, which is the generated assembly for the program at the top. This generated assembly, every time it's doing memory lookups with one or two exceptions, it's doing things like this. Right? So it's referring to something, it has statements like this. Right? And so it's using, instead of ESP, right, it is importantly not using ESP as the base for all of these variable storages and lookups. It's using EBP. Okay? And so that's sort of matching the picture we had above. You can start to get this idea in your mind that what this is going to look like is we're going to keep this picture going, and we're going to think of variables as lookups as starting at EBP and going up from there. Right? So that's the base for our variable lookups. So B, the first instruction of each function subtracts from ESP. There's a couple instructions in the generated assembly code at the bottom right. The first thing under F is sub ESP, comma 20, and the first thing in our main is sub ESP, comma 4. So there's something about subtracting ESP going on here. Those are the two functions that are in the program that's at the top center. There's something about subtracting ESP, and indeed, as we'll see, that's the goal of that is to make room for local variables. In C, if we look at the definition type in the abstract syntax, it is def of string expr. This is the function name. This is the single argument name. And this is the body of the function. Right? So C is not true. Right? There's only one spot for the argument to go. This string represents the argument. D, there is no way to define recursive functions in this compiler. I mean, how would you even go about answering this? Right? So this is asking basically, can you define a recursive function? Yeah? 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 Does it like, yeah, we'll see what it would mean for us not to be able to or to be able to here, right? Definitely, if we look at the function that's at the top of the page, so direct your eyes to where like it says def f at the top center of the page. Kind of looks like a recursive function. Uses f in the body. So if this works, we'll have recursive functions. So we'll have to think about what it'll mean for that to work. It turns out this recursive function will work fine. So we can define recursive functions here. So D is the other thing that's not true. We can totally define recursive functions using this. And in EAP, we also see that in the definition of this type, it's EAP of string, and this is the name of the function we're calling. So again, we can only refer to functions by name. This calls back to the representation I talked about at the beginning of Monday, where we're not doing anything where we can pass functions around as values here, pass functions into other functions, or store them in variables. They're just top-level names, right? Think about the top level of a C file. We just write functions at the top level, not in any other context. We can't pass them around. Okay. So that's some just high-level information about this compiler, just so we sort of read all the parts of it. Okay. So if I take the program at the top center, and I run it with input 4, passing in 4 as input into our main, what should the answer be? Should the answer be? Okay. 5, 4, 3, 2, 1. Okay. Talk about this for a minute. Okay, click in again. Click in again with the results of talking about this. Okay. 5, 4, 3, 2, 1. Okay. If we look at this function, you have to read a little bit of the assumptions on the worksheet, which is that if takes the false branch on 0, then otherwise. And so this is going to go into the false branch that returns 0 when x is 0, and otherwise it's going to add x to calling f on sort of x minus 1. So this is a recursive sum function. It takes in a numeric argument and recursively calls sum or f on one smaller number at a time and adds them all up. So this ends up computing plus of 4 plus 3 plus 2 plus 1 plus 0 all the way down. And that produces 10, because it's 4 plus 3 plus 2 plus 1, and that produces 10. It does not, importantly, it does not produce 0. We do go into the then branch over and over again and build up this accumulated sum. So this is the recursive sum. All right, and so hopefully it produces this when we step through making the compiler work. Okay, I want to pause here and just let you, there were some lingering conversations going on after we stopped. So I want to pause here for a second and just let you come up with any questions you have, because I have some questions I'm going to ask, but I want to make sure I clarify anything that's on the worksheet that you're looking at before we go on. So take a minute, look at the worksheet, talk about it for a minute, ask any questions you have about stuff you're still confused about on the worksheet. Some good questions we can generate here. Okay, questions that people have, Some of them we might cover in questions I have, but I want your questions, yeah. How would you do an else if? With this, I would, I'd probably, so how would you do an else if? I would write something like if, and then whatever condition I wanted, then the then branch, and then I'd just write a nested if here, right? And right? And so you can sort of think of it's like if, then, else, if this, then that, and eventually you get into the else branch. So, and if you wanted to add this to your language, right, you just need to design a concrete syntax for it, and then you know exactly what it should mean, right? You could have it be if, and then many pairs of condition and result, right? And that's like a chain of else ifs. And then you could turn it into that nested structure or compile it directly, right? So as a language designer, you'd have the freedom to pick how you wanted to do it. That's what I interpret as the meaning of an else if. Yeah. Other questions? Other questions? Questions? Yeah. 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 So the F, if you look at the concrete syntax versus abstract syntax, which is sort of the top left and right, you'll see that like the top is def fx, and that the corresponding part of that in the abstract syntax is a def, and that has f and x as the first two parameters to the def, right? And so those are being parsed and turned directly into those two parts of the function definition. And the program is just a list of these function definitions. I mean, we can, in let, we have a string, we have strings and they're in different amounts of parentheses. We can sort of, this is just up to how we implement parse, right, for which way we set this up, right? We don't have to say that because we put them in parentheses here, they must appear in a list in our abstract syntax. In the abstract syntax, there's just a name and a name for the argument. Yep. Yeah? Mm-hmm. So in the code for E to IS, which is, I just write that as short for expert to instructions because I want to fit it on the worksheet, you say, what does pushing after label do? I'm going to talk about that on the next slide. That's a good question. That's actually something I want to get out on the next slide. Other questions? So that's you're predicting the next one. Yeah. Yeah, so if you wrote a let inside a function definition, you could bind the same name as one of the parameters and shadow it. Yeah. I mean, you as the language designer could pick. That's the way we've set it up in the languages we're doing in this course. And that's pretty common in languages like, some languages just disallow it. They say there's two definitions of the same thing in the function. But if they allow it, that usually has that shadowing behavior where the inner one takes precedence. Okay. Yeah. Is it possible to do Boolean arithmetic now? Yeah, I simplified this language just so I didn't have to put all the tag checking and representation stuff on this worksheet. So in what we're talking about here, yes. But that's just, I mean, let me make a higher level comment. In the PAs, we give a specification for a language because we have to agree on something so that we can talk about what you're supposed to implement. In general, my higher level attitude is that making up a language, now that we're in a compilers class, making up a language is a cheap operation. I'll say that again because it's kind of an important high level concept. Making up a language is a cheap operation, right? Someone asked about else if, right? I can describe in about 2 minutes now what it means to add else if to the language. We pick an S expression structure, we think about how we'd put it in parse, we come up with its meaning in abstract syntax, and we know how we'd compile it through, right? So for this lecture, I made a worksheet where like Booleans or numbers are indistinguishable because I wanted to make sure the code would fit on a worksheet. And that's the context of this. And you know, now we can sort of get into this workflow where I can say, imagine a language where, right? And I'm starting to expect that based on your experience writing compilers, you can imagine a language where, right, as a relatively cheap operation for us to do. Okay. So that's a high level comment. Yeah. I'm sorry? Yeah. What's an expensive operation? I mean, designing a language to be good for particular users is an expensive operation. because you have to understand the population you're designing the language for. You have to think a lot harder about syntax and what they're going to be comfortable with. You have to think about what architectures it's going to run on and what environments it's going to run. So there's a lot of decisions that go into designing a language for particular users or particular applications. But if we're talking about pretty common programming language features like conditionals and variables and functions, I mean, functions are not cheap yet because we haven't really learned how to do them, right? We're sort of figuring that out right now. But those operations like arithmetic and ifs and bindings and things are starting to be pretty cheap, right? I mean, if it takes us a week to do them, in the broad scheme of things, that's pretty cheap, right? And in terms of imagining the implementation, that's something we're going to be able to do pretty quick. We're going to be able to say, I could think of taking the PA1 process and running it through. Okay. So that's sort of one of the high-level comments I want to make about the course is one of the things you should be able to do coming out of this course is if someone tells you about a new language, you should be able to start filling in the gaps in your mind of, oh, what's the implementation? What decisions did they make in the syntax? I can imagine that they probably used a strategy like this. They probably laid out the stack in some reasonable way, right? These kinds of things. Okay. So good questions. I'm gonna, that's sort of your question is the one that this next slide is about. And it has to do with, we'll have to interpret what these pushes do after we see what fills in here. But the next question is, based on the code on the left-hand side at the bottom, what would fill in for these four blanks in the body of F? So this assembly code underneath F is what we're generating for this function definition. So which one of these four is what fills in for the body of F? Five, four, three, two, one. Okay, just talk about this one for about 30 seconds. I'm just going to open this up for a little over 30 seconds more. So talk about it, convince yourselves, and click in again. Okay, another 10 seconds. 5, 4, 3, 2, 1. Okay, all right. So there's a couple clues you can use to pinpoint what's going on here. So there's some business with moving a bunch of values around, and there's some jumping that involves an else case and stuff like that up here, and some comparisons. So it seems like this part probably has something to do with the if comparison. Down here looks like it probably has to do with the else case. And so actually, let me shorten my little thing here. And this looks like it probably has something to do with being like the then case, right? All of this, all the way up until the else label. And so the stuff up there, well, there's a -1 going on, so that might be the arithmetic that's doing the subtract from 1. And then here, crucially, there's a jump to f, right? That's sort of the biggest signpost in this code that tells us where the different pieces of this are coming from. We know that one of the places where a jump shows up here is the code for eapp, because one of the things eapp is going to do towards the middle of what it does, or the end of what it does, is jump to the function we're calling. So the eapp case has the name of the function and the argument. It's going to do some work to set up the stack and then jump to that function. And we're going to expect that the function with that name is defined as a label somewhere in the file. So this means that this jump f here is where we're seeing part of the recursive call to f, right? Part of this recursive sum call to f. And we can see the other parts of this, this label after call 3, that's the after label here showing up as a label in the code. And then we see this pop EBP, and there's a pop EBP here as well. So we can see that this is sort of the end of a call. And so the stuff right before this should be the 4 instructions in the list we see right before it, which are these 4 instructions here. So push EBP doesn't depend at all on any context. It's just push EBP. It's just that instruction. The next thing is push whatever after label is. And after label had better be after call 3 in this case. I mean, that's the label that sort of corresponds to this chunk. We're using it in both of those spots. So we ought to then push after call 3. So we can ask what that does in a minute. And then the next thing is just this move into EBP, the value of ESP. And then push the value of EAX. And so push EBP is saying let's store the current value of EBP. We'll want that back later. Push after call 3, that's going to be the return address. So it's saying we want to save to the stack this instruction's address because we're going to come back here after we're done calling this function. Then moving ESP into EBP, now we're coming up with like a new base pointer. So we'll talk about that when we get to the next slide and draw this out. And then push EAX corresponds to the argument. So all the work from part of this work like here, like subtracting 1 from a value, all of this was calculating the argument to f in this recursive call. And so we're pushing that argument onto the stack, and then we jump to the function. Okay? So all this work is saving the base pointer, EBP, putting the return address on the stack, updating the base pointer, and we'll see what that looks like in the next slide, and then putting the argument on the stack and then calling. Okay? So this is the setup for a function call. All right, and also just mechanically, this is interpreting the OCaml code to understand what must have come out, right? Just as a mechanical process. Without interpreting these instructions at all, right? We can look at OCaml code and imagine what instructions must come out from it. Okay. All right. So the next thing I want to do is there's a couple different spots in this code where I want to fill in the stack. So the picture on the far left is actually what this looks like. I just opened up the debugger and made sure I had all these values right before I made the slide, right? This is what the stack looks like. This is like what C set up right when our code starts running, and that's in the very bottom right of your worksheet. So take a minute, locate the bottom right of your worksheet. Look at the code at the very bottom right of your worksheet. This is this label, our code starts here, and that's where the generated code you've been writing has gone, right at that label. And so the stack at that point, what C set up for the stack is there's the return address, and this is going to return back into main, right? So in main, there's some place where we call our code starts here, and that return address is stored at the top of the stack. Just below that, at one higher address, so this direction is increasing address values, right? Is the argument parsed input. That's where C put the argument when it called our code starts here. You'll notice that in the box on the upper right, there's code for main, and there's a call to our code starts here that passes in the value that came as a command line argument. And below that is just a bunch of stuff that main used, right? Like main's local variables and anything that the C or the operating system really set up for starting that call to main. But really relevant to us is that there's the return address back into main and then this input value that was parsed on top of the stack. So what I want you to fill in, and we'll do this one step at a time, but in the middle, I want you to fill in at the point where we get to our main, right at the top of our main, which is the another chunk of assembly you see there. What does the stack look like? What values have changed on the stack? Fill in any values that changed on the stack. And where do ESP and EBP point to? Where do they point to on the stack when control reaches the top of our main? What'll be on the stack? So think about that for a minute. Try and fill this in. Try and fill this in. What's going to be on that stack, in that stack in the middle when we get to our main? Person who just came in is like, oh, it's a pop quiz. Oh, no. Here you go. Yeah, no problem. OK, all right. So let's talk through what happens here. Does someone want to sort of get me started filling things in here? Get me started filling things in here? Get me started with this. What did you have in the box right above return address to main? It's in the box right above return address to main. Yeah. Parsed input. Let's see. So one option is, so I'm just going to put options here. I don't want to tell you if you're sort of shout out if you're right or wrong here. So right in this spot right above here, is it parsed input, basically copying, sort of copying that input value. Other ideas for what's right above return address to main on the stack. Right above return address to main. Yeah. No, you, yeah, go ahead. The current EBP value. Was that what you were going to say in the front too? Okay. Other suggestions for what could be right above return address to main? Cool, let's vote on these. So instead of bullets, let's just make this be A and B. Okay. What's going to be in this slot right above return address to main? 4, 5, 4, 3, 2, 1. Okay, so if we look at the code for our code starts here. First, we're saving something in EAX, and then we're pushing the current value of EBP. So this is the old or saved EBP value. So whatever address EBP held, which is basically the base pointer of main stack frame, that's going to be stored first, because that's the first push that happens, and that's the first thing that changes something in memory, because we're doing this push. So then the next push is a push of after main. And this sort of gets back to the question earlier about what does it mean to be pushing these addresses. Well, after main is a label. It's a label later on in our code starts here. So it's what's going to show up here is, I'm just going to write it as the label itself, is after main shows up here. But really, this is the return address for calling our main. So later in our main, we're going to use the ret instruction, and it's going to look up this code address, this label address, and jump there, right? So we're storing this on the stack because we're going to use the ret instruction later. Okay. And then the next thing that happens after we do this is we move ESP into EBP. We move ESP into EBP. We do these two pushes. And then the next instruction is moving whatever ESP is currently pointing at into EBP. That's interesting. Actually, at this moment, what is ESP currently pointing at? What is it currently pointing at? After we do these two pushes. Yeah. It's pointing to the top value on the stack. So push does the subtraction and then writes. It's actually really important if we think about what we said about valgrind, that push does the subtraction and then write. Because if it did the write before it did the subtraction, we'd be writing to addresses lower than ESP. So valgrind would complain on every push, right? So it's actually important that push is this subtract and then write. That's the order. And then pop is fetches the value and then adds. And that makes push and pop work like a stack. So ESP is currently pointing at this after main spot. And so if we move ESP into EBP, that means for a moment, these will both be pointing at this after main spot. So EBP will be pointing there. Then after we do that move, the next thing we do is we push EAX. What's in EAX right now? What's in EAX as this is running? What's in EAX right now? EAX. We moved something into it as one of the first instructions. Yeah. Parsed input. So the first thing we did is we grabbed the sort of the argument or the input value, stored it in EAX so that later we could push it. So then we end up with the copy of parsed input here, and then ESP is pointing to this spot. Okay? And then we do the jump to our main. So this is what the stack looks like at the top of our main. Right? That's what we set up for our main to use to jump into our main. Okay. Cool. So I'm going to give away a bit of the answer for this next part here. Actually, let's see.
Actually, I want to do the next slide. So I'm going to leave filling in what the stack looks like at the top of F, or at the beginning of F the first time for you to fill in. Because I actually want to do the next slide, and I think what I drew here is enough for us to talk about this, this next slide. I think this next slide is interesting to talk about. Okay? So the first question, you can ignore the questions below here for now. The first question I want to ask is, the thing at the top right, this is just like the C calling convention on x86, right? This is from that x86 assembly guide I gave you. So I just have that for reference because it's useful to think about what happens in C versus what this calling convention is doing. So which of these 4 pictures represents the calling convention on the worksheet, right? Sort of based on what we just saw. Which of these is what it's going to look like at the start of a function call? The start of a function call. Which represents what it looks like right at the point of jumping into a function. What is it going to look like? Okay. 5, 4, 3, 2, 1. And this is a good one to talk about. This is a good one to talk about. Okay? And you can use the code on the sheet to help you understand what it's going to look like, but it's a good one to talk about. Okay, clicking again. I'll leave this up for about 20 seconds. Okay, 5, 4, 3, 2, 1. Okay. So the code that we trace through in our code starts here is setting up what our main expects to see as the stack when it starts, and that's going to be what each call expects when it starts. And so the first thing that gets pushed is the old value of EBP, then a label gets pushed, and then the parameter. And in the middle of that, we save EBP to point at this return address. So the first value that gets pushed is EBP, then the return address, then we save EBP to point at the return address, and then we push the parameter, and so ESP is pointing at the parameter. So D is what happens in the calling convention on the worksheet. And I want to highlight the main difference between this calling convention and the C calling convention. Because, and we'll sort of wrap all this up on Friday to talk about the rest of these pieces, but I want to highlight this difference. We're about to use this space for the local variables of the function. Right? The function is going to start writing its local variables into this space. So there's the big difference. This is very much like the C picture, right? The big difference is that the parameter appears above the return address and the saved EBP. That's the big difference here, is that we're going to make use of this. It's going to actually really, really help us that these things are below the parameters because it's going to help us do a particular kind of optimized call. And that's the big difference between these pictures. So the main contrast between the way C does things and the way we're going to do things, and actually OCaml does something kind of like this, we are going to store that fixed size data of the return address and the saved DBP below the parameters and the local variables that the function uses. And that's the main distinction. So on Friday, we'll talk about calculating the space for the local variables and sort of finishing all this